So, hello dear students, hope you are in good health and so let us mark your attendance and just write your attendance in the comment box so that I can check how many students are online. So, in this today's lecture, so we are going to discuss a very important topic, that is the problem related to the topics which we have already discussed, like the nuclear forces, the binding energy concept, and the concept of fusion and fission, and related with this. And there are some problem that is related with the Heisenberg uncertainty principle, and this will help you to get to know that where you stand and what is your understanding in the concept. And whenever I ask a question, so you will try to solve this question and write your answer in the comment box, and then we will discuss that problem. So just keep yourself a copy and pen along with you, and you have to do some written work in this lecture. So how many students? There are only 8 students now. So we just wait for 1 or 2 minutes and then we will start our lecture. And in this lecture I will mark the attendance in between the lecture on the WhatsApp as well. So the first question is, the mean momentum of a nucleon in a nucleus with mass number A varies as. So there are 4 options which are given and you can check on your screen, and this is the question from GATE 2000 examination, and please write your answer in the comment box. So you have only 1 minute. So Jatin Sharma, Priyanka, Jaskirat, Supreet Kaur, Taranjeet Kaur, Shweta Sharma, Mandeep. So most of the students, so they are absent today. So I will give you a hint in this. So what is being asked? So you have been asked to find the momentum of a nucleon which is present in a nucleus, and you can use the Heisenberg uncertainty principle in order to solve this problem. So the what had the Heisenberg principle says that the change in position with respect to change in momentum, so that is of the order of h bar. So what does it means? So no two particle can remain at a same position at a particular interval of time. So ਉਹਨਾਂ ਦਾ ਜਿਹੜਾ momentum ਆ ਇੱਕ particular position ਦੇ ਉੱਤੇ it cannot be same. So from that, the change in momentum, that is with respect to time or with respect to distance, you can calculate. So we have to calculate the value of delta P, that is h bar over delta x. Now the nucleon which is present in a nucleus, the change in position, so that is of the order of the diameter of the nucleus. So the value of delta x, so it is of the order of 2 times the radius of the nucleus. So from here we all know that radius it is equal to r naught a raised to power 1 by 3, And so putting these values, so this equation becomes over 2r, that is 2r naught a raised to power 1 over 3. And when you can check, so the value of delta p, it is directly proportional to a minus 1 by 3. So the correct option for this question is option D. Yes, many of the students. So Vishali is correct, Jaskirat is correct. So next question is the mass of hydrogen atom, neutron and uranium 92 238. So they are given in terms of atomic mass units, and the binding energy you have to calculate using the binding energy formula. So calculate it. So this we have discussed. So for a uranium 92 238 nucleus, the value of Z, that is number of protons, so they are present is 92, and the number of neutron you can calculate, that is A minus Z, that is 238 minus 92, which is 146 neutrons. Now the binding energy formula that we know, Z into MP, here MP is the mass of proton, plus A minus Z, that is number of neutrons which are present, minus the mass of nucleus, that is the mass of uranium. So putting these values, 92 into mass of proton, it is given 1.0078, plus number of neutrons, that is 146, mass of neutron, that is 1.0087, minus mass of uranium nucleus, it is given 238.0508, and here the formula it is in atomic mass units, and the values they are also given in atomic mass units. So when you solve this, so it is coming of the order of 1.937 atomic mass units. But your values in the answer, you have to find it in mega electron volt, and we all know that the one atomic mass unit, that is of the order of 931.64 mega electron volt, and its value is given. So when we multiply this term with 931.64, so our binding energy comes out to be 1804.58 mega electron volt, and roughly, so you can check from the option, so which is the closest option, so that is again the option D. So there are only 2 or 3 students who has given the correct answer, so other also try to solve this problem, because these are the questions which generally come in the competition exams, and you can check that. So this is the question which comes 2 times in the gate examination, that is in the 2000 and in 2003. So next question is the volume of a nucleus in an atom, it is proportional to, so this is a easy question and you can solve it easily. So we all know that the nucleus, it is generally considered as a spherical body, and the volume of sphere, that is of the order of 4 by 3 pi r cube, and the value of radius we know, that is r naught a raised to power 1 over 3, and putting the value of radius in the volume formula, so this equation becomes pi r naught cube into a, where r naught is the standard radius, that is of the order of 1.2 femtometer, and you can check from here the volume, it is directly proportional to mass number. So the volume of volume for a particular nucleus, it is directly proportional to mass number. So option A is correct. Now next question is the related question which we have done in the previous slide. So if Me, Mp and Mh are the rest mass of electron, proton and hydrogen atom in the ground state, and the ground state energy of the hydrogen atom, that is of the order of minus 13.6 electron volt, it is given, and which of the option is true below. So you have to find the correct relation of the binding energy with respect to mass of proton, neutron and hydrogen atom. So just write your answer in the correct comment box. So again we will use the binding energy formula here. So the binding energy formula, that is number of proton into mass of one proton plus number of neutron times the mass of neutron minus mass of the given nucleus. So here you can see that this is our hydrogen nucleus, so we can write it as Mh, and for a hydrogen nucleus, so there is only one proton and one neutron that is present, and you can see, so this formula of binding energy, and for a hydrogen nucleus in the first orbit the binding energy is of the order of 13.6 electron volt. So here I want to mention one thing, that so in a hydrogen nuclei, so when it is present in the first electronic orbital, the electronic energy is, that is of the order of minus 13.6 over n square into electron volt, where n is the number of orbital electron की ਜਿਹੜਾ electron ਆ ਉਹ ਕਿਹੜੇ orbit ਦੇ ਵਿੱਚ ਜਿਹੜਾ present ਹੈਗਾ ਹੈ, and this negative sign, it represents that how much energy is required to ionize the electron from that given nucleus. And in common conversion we generally consider the unbound electron has zero energy, while the bound electron, it has some sort of finite energy, and for the electron which is present in the first electronic orbital, the ionized energy is, that is minus 13.6. Or you can also say that this is the separation energy required in order to eject that electron from that particular orbit, and the binding energy, it is the opposite of this separation energy. And so when we consider it minus of minus 13.6, so for the first orbital electron which is present in the hydrogen atom, so the binding energy, that is of the order of 13.6 electron volt. So putting these values in this equation, so binding energy is 13.6 electron volt, so Z is 1, so we can write it Mp plus, here again we are talking about the electronic atomic states, so we will consider, so that is the mass of electron minus mass of hydrogen and multiply by c square, because the binding energy is delta m into c square, where delta m is known as the mass defect, and this the Bragg term is the mass defect term. And when you write it binding energy to the right hand side, so the value of Mh you can write, that is Mp plus Me minus 13.6 electron volt over c square. So from here you can see that the option B is the correct option. So Ridhima, Supreet, Sakshi, Kajal, so all have given the correct answer. So moving towards the next question. So the order of magnitude of binding energy per nucleon in a nucleus, that is of the order of, so what will be the correct option? So we have discussed this binding energy per nucleon concept in detail, and what we have discussed, so that the trend of this binding energy curve, it is something like this, and if we are writing the number of atomic nuclei, so this side it is the binding energy, and the maximum binding energy, that is for iron 2856. So ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੀ maximum energy, that is of the iron, that is of 8.8 mega electron volt. So the order of magnitude of the binding energy per nucleon in a nucleus, so the closest choice, that is of the order of 10 mega electron volt, and this you can also calculate. So from the Heisenberg uncertainty principle, that is the wave mechanical consideration, so we can calculate the momentum of the nuclei, that is h over delta x, and delta x for a nucleus we know that is the 2 times the radius. So once we calculate the value of delta p, from that we can calculate the kinetic energy of that nuclei, which is p square over 2m, and delta p, that is h square over 2 r square, that becomes 8 m r square, and r again we know that is of the order of r naught, a 1 over 3 nuclei, 1 by 3. So putting the value for this iron, so you can calculate, so it is coming of the order of 10 mega electron volt. So this is in consideration with the proton neutron theory of wave mechanism. So next question is, a particle is confined within a spherical region of radius 1 femtometer. Its momentum can be expressed about, so what is given, so a particle is confined in a spherical nucleus whose radius is 1 femtometer. So you have to calculate the momentum. So how you will find it? So again you can use the Heisenberg uncertainty principle, that is h bar, or you can write it h over 2 pi, and the value of delta x now, that is 2 times radius, and radius it is given 1 femtometer, that is 10 is to power minus 15 meter. So this equation of momentum, it becomes h over 2 pi into delta x so we have to find this answer. Here the term that is present, the speed of light in the denominator, so you can multiply and divide this term with c. So putting these values, 6.63, 10 is to power minus 34 joule second over into 10 is to power minus 15 meter. So speed of light, that is 3 into 10 is to power 8 meter per second over c. So these are the values, so that comes in terms of joule, and it is coming out to be 3.167 into 10 is to power minus 26. So this minus 15 goes up, this becomes 10 is to power 15 times joule. So from that we know that 1 electron volt, so that is equal to 1.6 into 10 raised to power minus 19 joule, and 1 mega electron volt, that is of the order of 10 raised to power 6 electron volt. So 1 mega electron volt, it becomes 1.6 into 10 raised to power minus 13 joule. So when we divide this with this term, that is 3.167 into 10 raised to power minus 11 over 1.6 into 10 raised to power minus 13, 1 over C, this energy that is converted in terms of mega electron volt, and it is coming of the order of 1.98 into 10 raised to power 2 mega electron volt over C. So that is of the order of 200 mega electron volt over C. So from here the correct answer is option C. So students, write your answer in the comment box. So this is how you can calculate such type of numerical problems. So the next question is the mean kinetic energy of a nucleon in a nucleus of atomic weight A, which varies as a raised to power n, and where n, you have to find the value of n in terms of 2 decimal places. So again we have to calculate the kinetic energy of nucleon in terms of mass number A. So we have to derive this relation. So delta x delta p, that is of the order of h bar. So from that you can find the change in momentum, that is of the order of 2 times radius. So the kinetic energy, that is p square over 2m. So this equation becomes h bar square over 8m r square, and again the radius of nuclei, that is of the order of r naught a raised to power 1 over 3. So this becomes h bar square over 8m r naught square a raised to power 2 over 3. So the kinetic energy, it is directly proportional to a raised to power minus 2 by 3, and the value of a, it is varying as a raised to power n, and you have to find the value of this n. So the n comes out to be, that is minus 2 by 3, or you can write in 2 decimal places, that is 0.67. So this is you can see that how they can change the statement of a question and ask you anything related with this Heisenberg uncertainty principle concept. They can ask you the questions related with the binding energy. They can ask you the questions related with the mass defect. So if you are very much clear about these concepts, then you can solve such questions easily. So the another question that is related with the wavelength of the particle in a nucleus. So the question is, Compton wavelength of a proton is dash femtometer. So you have to find the wavelength of proton in terms of femtometer. So here I would like to explain that. So using the de Broglie hypothesis, we know that it is of the order of h over p. What does it mean? So this de Broglie hypothesis, it gave the concept of wave particle duality. So what he said, that the particle, it can exist it moves in the form of a wave packet, and it can act as it can act as a wave as well as a particle. So that is the concept of the wave particle duality. And if it is moving in the form of a wave and having some finite momentum, and from that you can calculate with which wavelength that particle it is moving. So the momentum of the particle we can calculate in terms of mc. So considering that the particle it is moving with the speed of light, so putting these values you can find out the wavelength of that particle. So mass of proton, that is 1.6 into 10 is to power minus 27 kg, and moving with speed of light, and from that so it comes out to be 10 is to power minus 15. So that is 1.32 into 10 is to power minus 15 meter. So the wavelength of that proton, so that is of the order of 1.3 femtometer, with which it is moving within the nucleus. So how many students? So they have marked the correct answer. Vishali is correct. Taranjeet is correct. So this is the question, the next question, which is in the NET CSIR 2011 examination. And what this question says, the radius of copper nucleus, it is given, and it is of the order of 4.8 into 10 is to power minus 13 centimeter. And from that you have to calculate the radius of magnesium nucleus. So radius of copper, so it is in two parts, so I will do a part here. So copper radius, it is given, so copper is 2964, and it is 4.8 into 10 is to power minus 13 centimeter. And you have to calculate the radius of magnesium, and we will use this formula considering the spherical nuclei. So radius is directly proportional to mass number, that is a raised to power 1 over 3. So radius of copper over radius of magnesium, that is mass of copper over mass of magnesium times 1 over 3. So mass of copper it is given 64, mass of magnesium it is given 27, and from that radius of copper over radius of magnesium, that is of the order of 4 over 3. So radius of copper is given, so from that you can calculate the radius of magnesium, that is 3 by 4 into 4.8 into 10 is to power minus 13 centimeter, and it comes out to be 3.6 into 10 is to power minus 13 centimeter. So the correct option is option C. Now in the second part they have asked the root mean square energy of a nucleon in a nucleus of atomic mass A in its ground state. So you have to calculate the energy of the nucleon, so which is present in the nucleus for a particular atomic number A that is present in the ground state. So again here you will use the total energy concept. So the energy, ground state energy of a nucleon, so it is P square C square plus the rest mass energy of the nucleon. So m naught C square here is the rest mass energy. So from that E comes out to be P square C square plus m naught C square the whole square. So energy, it is coming directly proportional to momentum. So once we find out the value of momentum, from that we can easily find out the energy. So the delta P, delta X, it is of the order of H bar. So delta P, it comes out to be H bar over 2R. So I will write here because there is some problem in writing. So delta P, it comes out to be H bar over 2 times R naught a raised to power 1 over 3. So delta P is directly proportional to a raised to power minus 1 over 3. So E comes out to be a raised to power minus 1 over 3. So again here I would like to mention that it is not the relation which you will find for the kinetic energy of a nucleon. Here it is asked the root mean square energy, that is you have to find the total energy of the nucleon and you have to use this formula. Otherwise if you use the kinetic energy formula, then the energy is p square over 2m, and that formula gives different result. So you have to use this total energy formula in order to solve the root mean square energy of a nucleon. And if so the option for root mean square energy, so option C is correct. And if it is asked the kinetic energy of the nucleus, then the option D should be correct. So these are some of the difference they can relate in the statement in order to confuse the candidates. So last question we will discuss related with this, that is in the TIFR 2013 examination, at 2012 examination. So a proton is accelerated to a high energy E and shot at a nucleus of oxygen. So we are shooting a proton that is having energy E to a nucleus of oxygen in order to penetrate to the Coulomb barrier and reach to the surface of oxygen nucleus. So what energy must be at least of that proton? So you have to calculate the energy of that proton, and I think I have discussed this problem so with you already, and you can find out the penetration energy, because now we are talking the Rutherford alpha scattering experiment, and the kinetic energy, it is being transferred to the potential energy of the particles. So here Z is oxygen that is given, so atomic number is 8. So from that you can put the values 8 into 1.6 into 10 raised to power minus 13 minus 19 square over. So here R, that is of the order of R naught a raised to power 1 over 3. A is 16. R naught we generally consider as 1.2 femtometer. So putting these values, so 4 pi epsilon naught, whose value is 9 into 10 raised to power 9, 1 over 4 pi epsilon naught is 9 into 10 raised to power 9. So R is 1.2 femtometer, that is minus 15 meter, multiplied by a raised to power 1 over 3. And when you solve this, it comes out to be 38.4 into 1.414 into 10 raised to power minus 14 joule. And in terms of mega electron volt, so you can divide this term with 1.6 into 10 raised to power minus 13, and it comes out to be 3.4 mega electron volt. So this is the minimum penetration energy required if the proton it has to transfer its energy to the oxygen. So that proton which is being shooted to a oxygen atom, so its energy should be greater than the penetration energy. So whose values it should be greater than the value of 3.4 mega electron volt, and you can check from these options which option is correct. So the option A is the correct option. So if that proton have to penetrate to the oxygen nuclei, so its Coulomb energy or its energy should be greater than the Coulomb barrier, that is of the order of 3.4 mega electron volt. So this is all about today's lecture. So there is one more question. So that is from the JEST 2016 examination, and it is saying that the stable nuclei that has one third the radius of OS 189 nucleus. So there is one atomic nuclei OS. I do not know what it is name. So but its mass number is 189. So you have to calculate the stable nuclei that has one third the radius. कि ਇਹਦਾ ਜਿਹੜਾ one third radius ਵਾਲਾ ਕਿਹੜਾ stable nuclei ਜਿਹੜਾ ਆ ਇਹਦੇ ਨਾਲ comparable ਹੋਏਗਾ. So again we know that R that is directly proportional to A 1 over 3. So R1 over R2 that is A1 over A2 the power 1 over 3. So first nucleus whose radius is 3 times the second, or you can say second has the one third radius of the first. So that comes out to be A1 is 189 over A2 the power 1 over 3, and from that you can derive that 27 A2 that comes out to be 189, and the mass number of the second nucleus whose radius is one third of the previous nucleus, that is 189 over 27, that is 7. So whose mass number is 7, that is the lithium nuclei. So the most stable nuclei of the radius that is having the one third radius of this nucleus which can interact. So our answer is lithium. So this is how you can solve these problems. So if you have any doubt, you can write your answers in the comment box, and within 5 minutes we will discuss uh, some of your queries if have on Zoom meeting. So see you on Zoom in 5 minutes. So till then, goodbye.